In the previous lecture, we were discussing the unary and the binary systems. Unary systems are the ones which is made up of a single component. That means you will have pure elemental solid. For example, you have say copper, then you will have precise melting and boiling points. So if I consider say copper, whose melting point is 1085, so below it, copper will be in the solid state, while above it, copper will be in the liquid state. Likewise, in case of nickel, nickel has its melting point at 1453 degrees centigrade. So below which nickel will be in the solid state, and above this temperature, nickel will be in the liquid state. So for single component systems or isomorphous systems, we have unique and sharp melting and boiling points. Now, an interesting question is, if I mix copper with nickel and makes an alloy out of it, what will happen to the melting point of its constituent alloy? So let's see. Instead of a single component system, we make a binary system which is made up of two components, but they have complete solubility amongst each other. Then they make a single phase which is called isomorphous. So if the solid is in a single phase but made up of two components, then it is referred as binary isomorphous system. One of the example of a binary isomorphous system is you take certain amount of copper and mix it with nickel. So the alloy that you form has two components and one solid single phase, which is a homogeneous mixture of certain amount of copper in nickel. So what will happen to its melting point? If you go with the unary system, where copper has a unique melting point of 1085 and nickel has unique melting point of 1453 degrees centigrade, we expect that the melting temperature of the formed alloy will vary along this dotted line depending on its concentration. So if I have 0% nickel, that means pure copper, my melting point is sharp 1085. If I have 100% nickel, that means no copper, then my melting point will be same as the melting point of nickel, which is 1453. And if I have some unknown proportion of nickel present in copper, then my melting point lies anywhere between 1085 to 1453. An interesting question is, above this dotted line, you have a single phase of liquid, and below this dotted line, we expect a single phase of solid. So do we get sharp melting point like the one that we have in isomorphous systems of copper and nickel in binary system as well, where the constituent solid is made up of more than one component? Answer is no. You do not have sharp melting and boiling points the way we used to get in the previous case. For a binary isomorphous system, what you get is a liquidus line. That means above which the entire phase is single liquid phase. The liquidus line runs from 1085 degree, which is corresponding to the melting point of copper, and goes on the other side to 1453. So on the top of this, we have a single phase, which is homogeneous liquid phase. You can see your liquidus line starts from here and it ends here. In the same manner, the solidus line has certain width, it is away from the liquidus line by certain magnitude, below which your entire phase is a single solid phase. So you get a complete solid below this particular line. What happens in between these two lines? In between the liquidus line and the solidus line, we got a semi-solid product. That is, your alloy is partially in a solid phase and partially it is in a liquid phase. So if you are somewhere here, you get alpha plus L phase. So in a binary isomorphous system, you have only one physical state of the matter present, either the liquid or the solid above and below the liquidus and the solidus line, and in between it has both the phases present, where the phases are, one of them will be a liquid phase, another one is a solid phase. Let us look at the phase diagram which is shown to us in the this particular PPT, and we try to answer the following questions. The first question is, what can we learn from these phase diagram? If the first question is, the phases presents at point A and point B. If you focus on point A is here. So where we are well below the solidus line. So the phase which is expected here is only the solid phase, which is alpha. So at point A, our answer is the phases which is present is the solid alpha phase only. At point B, at this particular point, we are in a region which is surrounded by liquidus line on one side and solidus line on the other side. So we expect two phases to be present, namely the solid phase and the liquid phase. Now, out of the total mass, how much mass is in solid and how much mass is in liquid is not known, but the number of phases present is partly it is liquid, partly it is solid. The next query that we want to answer is composition of those phases. Now, typically, many students get confused by the term composition. Remember, composition means percentage of constituents making the solid. You have to find percentage of constituent which is making the product, not the percentage of solid and percentage of the liquid. We are asking percentage of components that is present. In this particular case, we have two components, namely copper and nickel. So if somebody asks the composition of the phases, you have to tell in what proportion your element 1, which is copper, and in what proportion your element 2, which is nickel, is present at given point. So if I ask you to tell me the composition of the product at point A. Now, where is my point A? My point A is here. And we are in a solid phase. So everything is solid. The objective is to find out the composition of the alpha solid at point A. Where is my composition? My composition is on the x-axis. So what I will do is, I will take an intercept from the point under interest on the x-axis. Wherever it intersects the axis, it will tell me the composition in the weight percent of the nickel. Why? Because our x-axis has units of weight percentage of nickel. So if I extrapolate point A on x-axis, you can read my composition to be equal to 60 weight percent. So at point A, my composition is 60 weight percent of nickel. So if I ask you copper, how much will be copper? Copper will be 100 minus 60, that is equal to 40 weight percent. So you can also write along with nickel the composition of copper. So 60 weight percent nickel and 40 weight percent copper is present in your product at point A. Next is, what is our composition at point B? So I'm clearing the dots. Now we have to find out the composition of point B. Now this is little tricky. Why? Because point B has two phases, namely the liquid phase and the solid phase. What we have been asked is not the composition of the liquid or the solid phase. Rather, we have been asked the composition of phases at point B. So we will talk about solid plus liquid together. So to find out the total composition at any time, you have to draw a vertical intercept from the point under interest on the x-axis. You got some point? This is something like between 30 and 40. So let's call it 45. So at point B, our composition is 35 weight percent nickel and rest is copper. So if you want to find out amount of copper, it will be 100 minus 35, which comes out to be equal to 65 weight percent of copper. Remember, whenever you have been asked to tell the compositions, you have to take vertical intercept from the point under interest directly on the axis. Whatever the intercept value that you get is the total composition, irrespective whether it is in the solid or liquid. If somebody asks you to find out the composition in the liquid and solid phase separately, we can do that. I will teach you how to do that at a later stage, but don't get confused at this point. If nothing is mentioned about the solid and liquid separately, you have to find the total composition, and total composition is nothing but the vertical intercept from the point under interest on the x-axis. Third is, you have been asked to tell amount of phases. Now, this is important. What is phase? Phase is the solid phase or the liquid phase, and within the solid, it could be alpha or beta phase. So phase is basically physically or chemically distinguishable region. So if I ask you to tell me the amount of phase present at point A, so the first question that you should answer is, at point A, how many phases are there? We have previously answered this. At point A, we have only one single alpha phase present, right? In this entire region, we have only alpha phase present. So what will be its proportion? If there is only one phase present, the proportion will be 100%. So at point A, we have 100% alpha phase present. Same way, what about at point B? Now at point B, your part of the phase is the solid alpha phase, and the remaining portion is in the liquid L phase. Liquid phase we note as the L phase. So we have two phases, namely solid alpha and liquid L. So they will be in some proportion. Part of it will be solid phase and part of it will be the liquid phase. So there will be some unknown proportion of alpha solid and liquid L. How to compute this when more than one phase is present at a point under interest? Remember, if you take the vertical intercept directly, what you get is the total composition and not the phase-wise composition, right? So to find out the phase-wise composition, the process is little different. We are looking at the same phase diagram in a magnified manner. we are focusing on the same point, which is point B on the phase diagram. I have shown it on the enlarged version of the phase diagram. So this is our point B. Whenever you have to find out the composition of the liquid and solid, what you have to do is you have to first draw the tie line from the point under interest. Now, what is tie line? Tie line is basically a horizontal line which is passing from the point under interest. This line will intersect the liquidus line on one side and the solidus line on the other side. So what we did, we draw a line which is passing from point B and it intersects with the liquidus line on one side and the solidus line on the other side. Once you draw this horizontal tie line, you have to draw 3 vertical intercepts, namely from one, that is where your tie line intersects with the liquidus line. So you draw this vertical line. The point where it intersects the x-axis will tell you the composition of the liquid phase. So this is your Cl, which is referring to the composition of the liquid phase. Likewise, I will draw another vertical intercept from the point under interest. I will draw another vertical intercept from the point under interest, which is point B on the x-axis. This will going to tell me an average composition. Your average composition is the total composition irrespective of solid or liquid, which is C0. And third one is you draw a vertical intercept from the solidus line. So your tie line intersect with the solidus line at one particular point, and you draw a vertical intercept from that particular point on the x-axis. Where it encounters the x-axis is your concentration of the alpha phase, C alpha. So what we did, we first draw the horizontal tie line passing from point B. So we get 3 important points. One, the intersection point at liquidus line. Second one is the intersection point with the solidus line. And third is the point B itself. So we draw 3 vertical intercept from these 3 points. The one coming from the liquidus line tells us the concentration of the liquid Cl. The one that comes from the solidus line will tell us the concentration of the solid phase, which is C alpha. And the one that is coming from the point B or point of your interest will tell you the overall concentration, that is C naught. Remember, all these concentrations have their units which is same as the units of the x-axis, which is composition weight % of nickel. So if I read this, my Cl in this particular example is coming out to be equal to 31.5 weight % of nickel. So my Cl is 31.5 weight % nickel. What does it mean? At point B, whatever is the liquid present, that liquid contains 31.5 weight % of nickel, and remaining, that is 100 minus 31.5 weight % of copper. In the same manner, the concentration of C alpha phase is coming out to be precisely equal to 42.5 weight % of nickel. That means whatever is the alpha solid present at point B contains its nickel, which is equal to 42.58%. The remaining is copper, which is 100 minus 42.58%. So what we have understood so far, I repeat, we have understood first how to tell or define the phases present. So for that purpose, what you should do is you should simply look in the region on the phase diagram. Whatever is the phase present, you have to define it, whether the solid phase or the liquid phase or solid plus liquid phase. Then we understood how to find the composition of the phases. So whenever you want to find out the composition of the phases, you have to draw a vertical tie line from the point under interest on the x-axis. Whatever is the intercept point is your composition. Remember, when I say composition of the phases, we are defining the total composition. We are not separating it as percentage of nickel and percentage of copper in alpha and liquid separately. If you want to find out them separately, then you have to do the tie line analysis. For this purpose, what we'll do is we draw a tie line from the point under interest. It will intersect on one side on the liquidus line, on the other side on the solidus line. You draw three vertical intercept, one from the point under interest, one from the intercept with the liquidus line, one from the intercept with the solidus line. The one that is coming from the liquidus line tells us the concentration of liquid. One that is coming from the solidus line tells us the concentration of the solid. And the one that comes from the point under interest tells us the overall concentration C naught. Now, once these 3 points are...
How did you come to know that along the intercept CL, it is 31.5% of nickel only and not copper?
It is because your x-axis is being defined as composition weight percent of nickel. So whatever the direct value that you got on the x-axis is the value of composition weight percent in nickel. See here.
Sir, can you switch to the previous slide?
Yeah, I can. Here it is clear in this slide. It is composition weight percent in nickel. So
Yes,
your
sir.
tie line represents the value of weight percent in nickel. Is it clear?
Yes, sir.
I'm now going back to the previous slide.
We know that the composition is 31.5%, as it is not written in x-axis.
That is 31.58% nickel and remaining is copper. Once you spoke about one element, the other component is already spoken, because second one is always 100 minus x. If first one is x, second one is always 100 minus x. So if somebody asks what is
asking about how can we know that it is exactly 42.5 and
not 42 or 43, that is what your question?
Yes, sir.
This is because this chart will be available on the graph paper. So you will have subdivisions running between 40 and 50, right? So you can get the precise value of the intercept,
Okay, sir.
right? So you can get the precise measurement. Okay, now I am going back to the previous slide. There was some query left. Okay, here it was.
Sir, here on the left you have written CU also, no?
Yeah, let me explain that. See, you have three entities mentioned here. In the center, it is written as composition weight percent of nickel. So your axis represents the weight percent of the nickel. Now, if I come on the extreme first end, that is at this particular point, where my value is 0. So 0 weight percent of nickel means what? How much copper?
100%.
100% copper. That is why it is mentioned here as copper. This line represents the value of copper. You can also cross verify it from here. See, this point is the melting point of copper. So your vertical line, this vertical line represents the phase of the copper. And this is its melting point, which is 1085. Above this, you can see everything is liquid. And below this, everything is solid. You can see there is a sharp melting point right here. In the same way, if I move on the other side, here, I have 100% nickel. That means 0% copper. That is why it is mentioned as nickel here. This vertical line, let me take another color. This vertical line represents the pure nickel. And you can see its melting point is here, which is 1453. So above this, you have one liquid phase. You can see in this region, you have only the liquid phase present. And below this, you have only solid phase present. Is it clear now? Is it clear?
Sir, this was already clear.
So what is the doubt
But the
now?
question was, ki,
Hmm?
sir, why didn't you take 31.5% of copper and sir, why have you taken that 31.5% of nickel and not copper? Because on the left you have written copper. So starting from the left, shouldn't it be 31.5% of
No.
copper?
For a time being, don't look at this and this number. What is your axis? Your scale is, your y-axis scale is temperature in degree centigrade, and your x-axis scale is composition weight percent of nickel. So when I read this as 20, what is the meaning of that 20? That 20 means 20 weight percent nickel. When I read this point as 40, what it means? It means 40 weight percent nickel. When I read this point 60, it means 60 weight percent nickel. Likewise, if I read this point,
Okay, sir,
it means
clear.
100 weight percent nickel, and on this edge, it is 0 weight percent nickel, means pure copper. And to represent that pure copper, we denoted it on the lower edge. Is it clear now?
Yes, sir.
Okay, so should we proceed further?
Yes, sir.
So up to this point, what we have learned to read from the phase diagram, the phases present, its overall composition, which is only the vertical tie line from the point under interest, then composition of the individual phases. Whenever you want to find out composition of the individual phases, you have to draw the horizontal tie line, and the vertical intercept from the liquidus line tells you the concentration of the liquid, and vertical intercept from the solidus line will tell you the composition of the solid. The one from the point under interest gives you the overall composition, irrespective of liquid or solid. Okay, so we did the exercise. We have determined the phases present at point B. which is alpha plus liquid. Now we want to find out its amount, that is how much a particular phase is present. Remember, don't get confused between two things. The activity that we did in the previous one, where you find out the composition of the solid and liquid. When I say composition, composition means how much is nickel, how much is copper. Now what we are finding out? Now we are finding out the amount of phase. Amount of phase. What it means? Amount of phase means in what proportion a liquid is present, in what proportion the solid is present. We will not going to talk how much is nickel and how much is copper. We are talking about how much is solid and how much is liquid at point B. It is clear to us at point B, part of the material is alpha solid and the remaining portion is liquid L. So now out of the total mass, let's say I have total mass 1 kg. And out of that 1 kg, 700 gram is solid. So how much is the liquid? Remaining 300 gram will be liquid. So that is what we want to find out. What fraction of mass is solid and what fraction of mass is liquid. The process is identical to what we did in the previous case. Here also, you have to draw the tie line from the point under interest. So what you get is basically a horizontal line passing from point B. It intersects the tie line on liquidus line on one side and the tie line intersects with the solidus line on the other side. So your first step is draw the tie line. Second one is now determine the distance from the point under interest, which is point B, to each of the phase boundaries. Your phase boundary is the liquidus line and the solidus line. So what we did is we have found out 3 vertical intercepts, namely CL, C alpha and C naught. This is the same thing that we did previously, right? Now you have to find out the distance of these phase boundaries from the point under interest. Our point under interest is point B, whose x-axis value is C naught. So if I want to find out the distance of point B from the liquidus line, I should find out the gap between the CL and C naught. So I take this particular gap, which I have defined as R. So R represents the gap between the point under interest and the liquidus line. In the same way, we have C alpha. So if I take the difference between C alpha and C naught, I will get the distance between my point under interest and the solidus line, which we define as S. So I get 2 quantities. First is quantity R, which represents the distance of point under interest to the liquidus line. So your R is equal to C naught minus CL. You can clearly see your R is equal to C naught minus CL on the graph. Likewise, you define the second quantity, which is S. Your S will be equal to C alpha minus C naught. So what we did, we draw the horizontal tie line. From there, 3 vertical intercept. From vertical intercept, we got CL, C naught and C alpha. From that, we define R and S. R is the distance between the point under interest to the liquidus line, and S is the point distance from the solidus line to the point under interest. ठीक है? So R is equal to C naught minus CL and S is equal to C alpha minus C naught. Now we want to find out the fraction of the solid and the fraction of the liquid which is present at point B. So we first define the fraction of the liquid which is being defined as WL equal to S upon R plus S. You should remember it like when you want to find out liquid, we take the ratio vis-a-vis to the quantity that comes from the solidus line. Solidus line के side वाली quantity क्या थी हमारी? वो थी S. So while computing liquid, your formula will contain S upon total, which is R plus S. So now if you substitute for R, S in terms of C naught and CL, your S is equal to C alpha minus C naught. Your S is this quantity. So that quantity will directly go in the numerator. This is your numerator, C alpha minus C naught, and your R plus S will be equal to C naught minus CL plus C alpha minus C naught. So your C naught gets cancelled. What you are left with is C alpha minus CL. So your R plus S is equal to C alpha minus CL. Now remember, in the previous slide, we computed the exact value of CL, C naught, and C alpha. C alpha was 42.5, C naught was 35, and C alpha was 31.5. So if you substitute these numbers, you will find out your percentage of liquid is coming out to be 0.68. And if you want to write it in the percentage, you have to multiply it by 100. So it will be equal to 68 weight percent. So out of the total mass, your 68% mass is in the liquid state. In the same way, we can also find out the weight percent of the solid phase. The solid weight phase, which is being defined as W alpha, is equal to, you should remember it like opposite in the numerator. So for the solid, we will take the distance which is coming from the liquidous side, which is R. So it is R upon R plus S. You substitute the value of R and S here and simplify it. You get your formula to be equal to C naught minus CL upon C alpha minus CL. So if you substitute C naught, CL, and C alpha, you got your solid phase proportion to be equal to 0.32 or say 32%. So your final answer is the amount of phases is, we have 68% of our mass is liquid and 32% of our mass is solid. Is it clear or is there any doubt?
Sir, clear.
So the formula you should remember like weight percent of liquid is equal to numerator side coming from the solidus line upon total, and weight percent of the solid equals to the distance coming from the liquidus line divided by total. If you remember it like this, you will always be able to define your R, S, C naught, C alpha, and CL accurately on the graph sheet. Otherwise, students will get confused. There is a 100% guarantee that there is one numerical question always present in the question paper where you have to determine the amount of phases present at point under interest. So you should be able to do this activity. Everybody should be able to solve this. Now, when I write the expression for weight percent of liquid and solid, I said it is R upon R plus S or S upon R plus S. How actually it came? How do I know that it is S upon R plus S for liquid and for solid it is R upon R plus S? Why it is opposite? That is how I ask you to remember it. So let's quickly look at the mathematics that will lead us to the same formulae which I have asked you to remember. So the mathematical derivation, a small one, which tells us this is called the lever rule. The idea of the lever rule is if I add up the mass of liquid and solid, which is WL plus W alpha, my total fraction should come out to be equal to 1. Why? Because if I add up the two components, I will end up to the 100%. So WL plus W alpha, which are fraction of masses, if I sum them up, my sum of the fractions will be equal to 1. Now, WL, which is the weight fraction of the liquid phase, is equal to WLCl, that is weight of the liquid multiplied by its concentration, plus W alpha is equal to W alpha C alpha, which is equal to weight of the solid alpha phase multiplied by its concentration. If I sum them up, I will end up to my total concentration C naught. Remember, my total concentration C naught is sum of the solid plus liquid. But from the first expression, I can rewrite for W alpha as 1 minus WL. So if I now substitute this 1 minus WL in my equation 2, I can eliminate W alpha from equation 2, and it comes out to be 1 minus WL into C alpha plus WLCl equal to C naught. If you solve this expression for WL, it will come out to be equal to this quantity. WL is equal to C alpha minus C naught upon C alpha minus CL. And now if you substitute this quantity in the previous expression, you can again find out the quantity W alpha, which will come out to be C naught minus CL upon C alpha minus CL. If you compare these quantities with previous ones, remember this WL is C alpha minus C naught upon C alpha minus CL. I'm going back to the previous slide just to show you. You can see here your WL, this quantity is equal to C alpha minus C naught upon C alpha minus CL. So it is same as the one that we derived from the lever rule. So whether you do the derivation or you remember the way I tell you, for liquid, you should consider the distance from the solidus line, and for solid, you should consider the distance from the liquidus line. You end up with the same set of formulae. Your formula will be this one. Is it clear?
Please explain equation number 2.
Speak little loud.
Sir, please explain equation number 2.
Equation number 2. Okay. You got the first equation, WL plus W alpha, that is
Yes.
the fraction of the liquid mass plus fraction of the solid mass, that is equal to the 1. Now, if I want to define C alpha as the concentration of my phase, let's say my phase under interest is the nickel. I can talk in terms of any one of them. So I am talking in terms of the nickel concentration in the solid alpha phase. I define the concentration of nickel in the alpha phase as W alpha. Remember, C alpha. On the graph, we find out this concentration. C alpha was concentration of the alpha phase. It represents percentage of nickel. So C alpha is the concentration of nickel in the alpha phase multiply it by W alpha. What is W alpha? W alpha is weight fraction of the solid. So if I multiply weight fraction of the solid with the concentration, what I get is my total concentration of nickel in the solid phase. So this gives me the total nickel in the solid. Same way, if I multiply WL with Cl, where Cl is the concentration of nickel in the liquid and its weight fraction is WL. So if I multiply WL with Cl, this gives me total nickel in the liquid. So your first fraction, your first term is the nickel in the solid phase. This is nickel in the solid phase. This one, the second term, is nickel in the liquid phase. So if I sum them, I will get the overall concentration, that is total nickel at point under interest, which is C naught. Is it clear now?
Yes, sir.
So using lever rule, you can always define the weight fraction of liquid and the solid present. Okay, we are running out of time, so I am closing this session now. We will continue to solve few more example problems from representative phase diagrams, and we'll also talk about the microstructures which the solid possess in different phase conditions. That we will discuss in tomorrow's class.